Hello everybody, welcome to this talk on AI in Wargaming. I'm James Goodman, and while I'm presenting this today, it is very much a collaboration with Professor Simon Lucas at Queen Mary and Sebastian Risi at the ITU in Copenhagen. It is based on a report commissioned by DSTL to ask the question, what can we learn from the many recent successes that deep learning has scored in Go, StarCraft and other games? What can we apply to war games and what is less applicable? Specifically, this applies to computer-moderated war games, not physical ones. This short talk is a very high-level overview and is really the accompaniment to the full 50-page report that is freely available on arXiv. What I would like to do is broadly mention some of the headline successes that deep learning has achieved in games, and consider which aspects are relevant to war games, which ones less so, and then look at a number of areas that we think are of particular interest where war games have features and challenges that make certain algorithms more relevant than others. From a game perspective, the deep learning revolution started in 2015, 5 years ago, when DeepMind got to human-level play in a variety of Atari games from the 1980s. Only a year later, their AlphaGo beat the world Go champion. Then last year, after considerable investment, DeepMind's AlphaStar learned to play the commercial real-time strategy game StarCraft 2 at World Championship level. And on the right, also last year, OpenAI were able to beat the Dota 2 world champions in a highly competitive esport after a 3-year research effort. Now, at first glance, StarCraft and Dota 2 look much more similar to war games than Go or Atari. They're, for example, unit-based with partial visibility. The Dota 2 AI was able to beat the world champions and 99.4% of human players, but took 10 months of training to get to that level of performance. And each of the agents in StarCraft had the equivalent of 200 years of gameplay in real time. That takes hardware. On the right-hand side is the cluster that ran AlphaGo when playing the world champion. That's not necessarily what you're going to have for every opponent in every wargame. The power needed has come down. AlphaZero, the most recent iteration of AlphaGo, used only 1/8 of the compute power to achieve the superior performance. So there are ongoing algorithmic and hardware improvements, which are making this process cheaper and cheaper. But even so, one run of AlphaZero cost up to $250,000 to learn to play a game. This architecture is a high-level view of that used by OpenAI in Dota 2. It has 159 million parameters, but even so, many of the game aspects were controlled by hand-designed scripts. That 10 months of continual learning only covered certain aspects of gameplay. Others were human-designed heuristics. The money and time invested in DeepRL has led to huge advances in general-purpose reinforcement learning algorithms, and there are now several open frameworks and software libraries that make this accessible outside of full-time academic research. TensorFlow is the most famous from DeepMind, but you also have things like OpenSpiel from Facebook or the Fiber framework from Uber, which allows easy scaling of machine learning approaches across distributed clusters. This means the engineering efforts for large-scale AI computing have come down very significantly in software and hardware terms. You don't need a team of highly qualified academic researchers to implement the algorithms, but you can use software engineers with an understanding of machine learning to integrate with the available tools. However, we should bear in mind that much of this work, especially for DeepMind, is focused on the artificial general intelligence agenda. It's a key reason they focus on raw pixel input to use as little domain knowledge as possible. Similarly, I mentioned Uber's Fiber framework. Much DeepRL work is funded from a self-driving car or robotic control perspective. Here we have a similar situation where the actual input is direct sensor data from camera, radar, or LiDAR, and much of the work is on a model-free basis where the model of how the world works has to be learned from that data stream, implicitly or explicitly. Computerized war games are different to the extent that we do have a clear forward model, we know the rules, and we don't need to learn a full representation from scratch. We can skip the part of deep learning that learns what does a tank look like or how do we move the camera, and we can code that domain knowledge in right from the start, potentially saving significant time and resources. Another thing the headline results often have in common is they focus on world championship performance in a single domain. We don't generally need that with war games. The purpose of an AI in a war game can vary, but often we want an opponent that is sufficiently competent and realistically human-like to be a useful training environment without needing expensive humans to take on every role. Alternatively, we might use it to explore possible strategies, but we're still not looking for World Championship performance to make the optimal move in every position. So having covered some of the high-level conclusions on the applicability of the deep RL revolution, this second part of the talk is by far the briefest. In the accompanying report, we've categorized the common research environments on a number of different dimensions to highlight the extent to which they are comparable to war games. This table shows in green those that are qualitatively more like war games, and areas in red are less similar. Unsurprisingly, you can see that StarCraft and Dota 2 are more similar than chess or Go, but there are some areas that we should pay attention to the other environments and the techniques that are useful there. For example, win conditions are often a lot more complex and more wargame-like in some Atari games than in StarCraft or Dota 2, where it's a binary win-lose without any auxiliary goals or score. For more detail on these 14 dimensions, please see the full report. Now, the purpose of this categorization is to draw out specific features of wargame that can be challenging for AI, and then look at some techniques from the academic literature that we think are helpful to address these. Now, this table doesn't go through every single AI technique, but those we think are especially relevant, and to explain why they're relevant. I'm not going to go through this in detail given the time, but what I want to do today is take a quick look at the first three in a bit more detail: forward models, unit-based, and large action spaces, and then finish with a case study that combines several of these in a single example. An important difference between war games and many deep reinforcement learning applications is the fact that we have a forward model. This means we can use planning algorithms. This wasn't possible in StarCraft or Dota 2 as the rules are hidden in proprietary software, so DeepRL has to learn purely by trial and error. This approach was, however, used in AlphaGo, where Monte Carlo tree search was crucial and often an underrated part of their success. What this means, in essence, is that if we are sitting at the blue circle in the top right as our current state, the current position, we don't need to take every action in the actual game to find out what would happen, but we can imagine or plan with the green boxes what would happen if we take action A and then action B, and work our way into the future down the tree. With a fast forward model, we can run several thousand game simulations per second, which provide data on what-if planning scenarios to construct the tree in green. And we can use that analysis to take the best action that we think we can take in the actual game. This is closely related to the classic search algorithms used for World Championship chess AI back in the 80s and 90s, but it copes better with stochastic environments and explores the game tree in a more efficient and asymmetric fashion. As you can see here, we've investigated the left-hand track much more deeply than the middle or right-hand possibilities. Combinatorial multi-armed bandits are particularly relevant in this regard as they're explicitly unit-based. If we consider war games with multiple units, there are far too many options to be able to search effectively. Even a simple case of 3 units with 3 actions each would give us 9 different global permutations, and that gets worse exponentially. The CMAB approach plans for each unit individually and then combines those into a global action. So initially, we select an action for each unit from its own planning tree shown on the left, and combine these to give a global action in the main planning tree in the middle. We avoid a full search of all possible global actions. Now, initial combinations rely on a very naive assumption that each unit acts independently. But over time, as we run more simulations, actual interdependencies, for example, between nearby units that can support each other, will emerge and be exploited. Planning and deep learning are not mutually exclusive, and 2 particular techniques in the literature can be relevant. The first here is to learn the forward model using RL, and then use that learned forward model for planning. It's something, for example, that DeepMind have used in a further iteration of AlphaZero, but it is an emerging area and primarily useful if we don't have the rules up front. That's less common in war games, but hypothetically, if we had a slow legacy game engine, then this approach could learn a fast approximation to it and then use that for forward planning. The second approach is perhaps more generically useful. Expert iteration combines forward models and planning with deep learning and was central to DeepMind's Go success. The idea is that you can improve your search with an evaluation function that determines the value of a node in the game tree. Instead of using a handcrafted heuristic, the idea with expert iteration is we learn that function from scratch. Firstly, we run several games using Monte Carlo tree search or any other method, allowing a lot of time to make each decision. Initially, we just use a random playout. Then for each of those decisions made in the game, we record the state, the action, and the score obtained to give us a set of training data that we apply deep learning to learn an approximation function Q that estimates the score we will get for taking any particular action A from any state S. And the crucial point is that this function is a neural network that will return an answer in milliseconds, whereas the original planning takes seconds, minutes, or even hours. We can then use this Q in the next iteration of Monte Carlo tree search as a proxy for the value of each state, which will give us a better player and a better estimate of the action values. We repeat this process until we get convergence, and then we use the final function in the actual game, or rather as an evaluation function when planning in the actual game. You can often get the same performance in milliseconds using a good trained function this way than seconds or minutes of classic Monte Carlo tree search. A common motif in wargames is that we have many individual units. It's one of the clearest differences with much of the headline research. StarCraft does have distinct units, but AlphaStar fundamentally ignores that and learns a global strategy of where to move and click with the mouse from the visual field, either the same micro actions that a human player makes. Any understanding of units is implicit and is deep in the structure of the neural network. Looking at each unit individually is a natural fit for wargames, and often we actively want units to have autonomy, each unit acting only on the local information that it can see. We have two broad families of approach here. One is compositional, where each unit plans separately. We looked at combinatorial multi-arm bandits as an example of this, but it's far from the only one. And the second approach uses hierarchical techniques, where we split the decision-making into levels. We add a new brain at the top level, which represents, if you like, headquarters, that decides on a strategic plan or objective. And then each individual unit at the lower level makes its own decisions based on that general goal passed down. The top level might learn which reward to set. For example, if the current strategic aim is to retreat, then the reward function would encourage progress towards a rendezvous point while avoiding contact with the enemy. If we shift to a strategic goal of taking a location, then that might cause us to reward causing enemy casualties and moving towards that location. In either case, the individual units decide what to do based on local information to achieve that goal. Wargames have a huge branching factor, and action abstraction can be relevant where we can inject domain knowledge to reduce that. If, as in here, you are consider every possible action for every possible unit, then planning methods just can't search very far forward, and RL methods are prone to getting stuck in suboptimal solutions. Now, in practice, a human is never going to consider every one of those red arrows, but they'll consider just 2 or 3 sensible actions. For example, they might consider attacking the nearest unit, taking cover, or supporting a nearby friendly unit. Each of those action abstractions can be converted into a concrete action to take. This means that rather than considering the complete set of 20 different moves that are physically possible for each unit, we just consider the 3 or 4 that correspond to an abstracted objective. There is a risk that we lose an optimal action that involves some combination of rather obscure moves, but assuming that the injected domain knowledge is sensible, that risk should be small. So let me put this together and try and finish with an example that combines a hierarchical approach and deep learning and forward planning and action abstraction together in a real-time strategy game. And a central message to take away is that you can hybridize all these techniques. They often work better when combined, and it's certainly not a case of either or. This uses MicroRTS, a game that covers the essential mechanics for a real-time strategy game. This is a square grid, square movement grid, And each of the little circles represents a unit with the colours and the sizes being different types. The units move around, build the bases in white, gather resources from the areas in green. And you can see one of the orange ones has taken some damage with a green-red health bar. Here, our strategic target is to destroy the enemy base, the white thing. And tactically, we need to issue orders to each of the units separately and simultaneously. Initially, the approach uses a deep convolutional neural network that takes in the immediate surroundings of each unit, shown by the blue square, and picks which of 4 scripts to execute. The selected script is applied to the unit to return a specific action to take. Now, these are user-defined heuristic scripts for various attack, retreat, or resource gathering strategies. That gives us a list of 1 action per unit, which we then take forward into a second phase. The intuition is that units that are close to each other or to the enemy could benefit from coordination and a more considered and planned approach. So for this subset of units, we use a combinatorial multi-arm bandit for forward planning, so that that cluster of units can coordinate effectively, such as by concentrating fire. This example had a competition limitation of 100 milliseconds permitted for every move on a single CPU. That's a little artificial, but focusing the computational budget on areas that need to coordinate is generally valid. And it does make the point that you don't need banks of GPU clusters. So that was a quick look at one example from 3 of the main areas covered in the report. In overall conclusion, there is much that is useful in the spate of advances in deep reinforcement learning, but don't get too seduced by the artificial general intelligence agenda that inspires much of it. When applying AI to a specific domain problem, we do not, and probably should not, learn everything from scratch. There is a lot more detail in the report currently in archive. I have not had time to talk about partial observability, multiple victory conditions, human-like play, or information flow, for example. So please do have a look at that report if there is anything there that has piqued your interest. Thank you.